Now it is your turn to practice. There are 3 lab exercises to help you build recursion into real code. This is lab 1. You have about 20 minutes. Your goal is to write recursive binary search yourself, using the base case and recursive case template. Then check that it agrees with the iterative binary search from Chapter 2. This is the function to implement. It is called binary search rec. It takes the array a low index, a high index, and the key you are looking for. It works over a sorted array. Tested on 4 cases: the key at index 0, the key at the last index, a key in the middle, and a key that is not there at all. For the missing key, you should get back -1. One hint before you start: write the base case first, the empty interval, where low is greater than high. Getting the base case right first stops the reached after bug we just saw. Pause the video and try it now. Ready to compare? Let us walk through one clean solution. The first thing the function does is the base case. If low is greater than high, the interval is empty. The key is not here, so we return -1. Next we find the middle. We compute mid as low plus the quantity high minus low over 2. This form avoids overflow on very large indices. Now we check the middle. If a at index mid is equal to the key, we found it and we return mid. That is the second base case. If a at index mid is less than the key must be in the right half. So we recurse on mid plus 1, up to high. Otherwise the key is in the left half. So we recurse on low, up to mid -1. Each call shrinks the interval, so we always move toward the base case. Here is the output. Searching for 2 gives index 0, the first element. Searching for 72 gives index 8, the last element. Searching for 23 gives index 5, a key in the middle. And searching for 17, which is not in the array, gives -1, just as we planned. This matches Chapter 2's iterative binary search on every input. Same invariant, different memory. The recursion uses the call stack, where the loop used a while loop. This is lab 2. You have about 25 minutes. The goal is to make the frame stack something you can actually see. You do this by making 2 recursive functions print every call and every return. Add a depth parameter to factorial and to a simple recursive Fibonacci. Fibonacci of n is Fibonacci of n-1 plus Fibonacci of n-2. On the way in, print call f of n. On the way out, print return v from f of n. Indent each line by the depth, so the nesting shows. Then run factorial of 3 and Fibonacci of 4. From the printout, draw the frame stack for factorial of 3 by hand. One thing to watch: Fibonacci makes 2 recursive calls per frame. At any moment, only one path from root to leaf sits on the stack, but the total number of calls spreads out into a tree. Look for that in your printout. Pause and try it now. Let us look at one solution together, and then read the trace it prints. This is the traced Fibonacci. It takes n, and it also takes a depth, so it knows how far to indent each line it prints. On entry, it prints call fib of n. That is what this comment stands in for. Then it computes the result. If n is less than or equal to 1, the result is just n, that is the base case, and it makes no further call. Otherwise the result is fib of n-1 plus fib of n-2. That is 2 recursive calls from one frame, each with depth plus 1. Before returning, it prints return v from fib of n, so every frame prints once on the way in and once on the way out. Now look at what that costs. Fib of 1 runs 3 times, fib of 2 twice, and fib of 0 twice. Each one is its own frame, never shared. Those repeats are why the simple Fibonacci is slow. Here is the first half of the trace for fib of 4. Read the indentation as depth on the stack. The outermost call is fib of 4 at depth 0. Fib of 4 calls fib of 3 first, one level deeper. Fib of 3 calls fib of 2, deeper again. 3 frames are alive now. Fib of 2 calls fib of 1. That is the deepest point in this part of the run. Fib of 1 is a base case, so it returns 1 straight away, and its frame is gone. Then fib of 2 makes its second call, fib of 0. That is also a base case, and it returns 0. Now fib of 2 has both answers. 1 plus 0 is 1, so it returns 1 and its frame is popped. Back in fib of 3, the second call runs, fib of 1. It is a base case again and it returns 1. Fib of 3 now has 1 plus 1, which is 2, so it returns 2. That finishes the left side of the run. Here is the rest of the trace. Fib of 4 now makes its second call, fib of 2. This fib of 2 calls fib of 1, which returns 1. Then it calls fib of 0, which returns 0. So this fib of 2 returns 1 as well. And finally fib of 4 adds 2 plus 1 and returns 3. Now compare the two halves. This right-hand fib of 2 repeats work the fib of 3 side already did. The same small problems, computed again from scratch. That redundancy is why the simple Fibonacci grows exponentially. Here is the part people mix up. The full run of Fibonacci is a tree of calls, but the call stack holds only one path of that tree at a time. On the left is the complete call tree for fib of 4. It has 9 nodes. Fib of 1 appears 3 times, fib of 2 twice, and fib of 0 twice. The same small problems are computed again and again, and the tree grows exponentially with n. On the right is the stack at one moment. Only one path is live. Fib of 4, then fib of 3, then fib of 2, then fib of 1. The tree is the whole history. The stack is just the single path that is running right now. This is Lab 3, the challenge. You have about 30 minutes. The goal is to take the push while descending, pop while unwinding technique from the operations section and apply it to a different function. This proves the technique generalizes. The function is sum2. Sum2 of n is n plus sum2 of n minus 1, and sum2 of 0 is 0. It is not tail recursive. The plus must wait for the recursive answer, exactly like the times in factorial. Rewrite it as sum2 explicit stack, using your own array-based stack. Then check it matches the recursive version for n from 0 to 5. Reuse the two-face shape. Push while you descend to the base case. Then pop and combine while you unwind. Only the combining operator changes. It is a plus here instead of a times. Pause and give it a try. Let us look at one way to write it. The descending phase comes first. First we guard the input. If n is negative or bigger than max depth, we reject it and return -1. Max depth is the size of our array, so this check also keeps the array from overflowing. Then we make our own stack. This line declares an array called stack, with room for the deepest call we expect. Top starts at -1, which means the stack is empty. Now the descending phase. While cur is greater than 0, we push cur and then decrease it. This does the same job as the recursive calls going down toward the base case. Pushing means we store cur in the next slot. The plus plus is written before top, so top moves up first, and then we write into the new slot. Then cur goes down by 1, ready for the next push. The unwinding phase is on the next slide. When cur reaches 0, the pushing stops. We set result to 0. That is the base case value because sum to of 0 is 0. Now the unwinding phase. The loop runs while top is 0 or more, that is, while the stack still holds values. Each time around, we add the top value into result and pop it. The minus minus is written after top, so we read the top slot first and then lower top. This does the same job as the returns adding up. Then we return result. Here is the check. For n equal to 0, the recursive version gives 0 and the stack version gives 0. They match. For n equal to 3, both give 6. That is 3 plus 2 plus 1. And for n equal to 5, both give 15. Every case matches. It is the same descending and unwinding shape as factorial with an explicit stack. Only the combined step changed from times to plus, so the technique transfers directly.